Okay, so I'm not sure why my video got messed up, but apparently you didn't see, you got to see all of this, or most of this, how we figured that out. That's fantastic. So the end of page 2. But you didn't get to see me do any of this. So let's talk about what's happening here on page 3, which says it's page 4. Um, so beryllium, 4 protons. Um, 2 electrons, so I know it's got 2 more protons than electrons, so I know that it's positively 2 charged. And it's the symbol, which if you don't know, beryllium is right here on the periodic table, Be. So it's Be plus 2, and that's a cation. And I can check and go beryllium plus 2. Oh yeah, that's exactly what happened. And then chlorine, which has 17 protons, which I can just look and make sure that it has 17 protons, 18 electrons. If it has one more negative charge than positive charge, then I know it's -1 and it's an anion. Phosphorus has 15 protons right here on the periodic table. 15 protons, 18 electrons, so it's got 3 more electrons than protons, so it's P3 minus anion. And oxygen has 8 protons, 10 electrons. So it has 2 more negative charges than positive charges, oxygen 2 minus, and I can check and make sure that that's true. That is true, and so it is an anion as well. Explain how you would calculate the number of protons, neutrons, and electrons for the ion Al3+. And I said the protons from the atomic number, so Al 13 protons. Neutrons from the most abundant isotope. So if I round this into a mass number and make it 27, then 13. 27 minus 13 is 14 neutrons. That's what I got. And electrons for the ion Al plus 3. Well, I know that A equals P equals E in a neutral atom, so I know this has 13 electrons and 13 protons. But in order to get plus 3, I also know that I subtract 3 electrons. So if I have 13 and I subtract 3, I have 10 electrons. And that's how I got 10 electrons, by subtracting 3 electrons. Compare and contrast atomic number, mass number, and average atomic mass. So atomic number is the number of protons. Mass number is the protons plus neutrons. And atomic mass is the weighted average mass of all isotopes. It's that thing where you convert the percentage to a decimal and multiply it times the mass and add all your masses together. It's not one individual isotope. This is not one isotope of copper. This is an average of all the isotopes of copper. So it doesn't really tell me about all the isotopes of copper. Okay. Atomic mass is weighted average mass of all isotopes. So we got that. Identify the 2 values shown in the periodic table for each element. So we have the atomic number, which is the number of protons, and we have the average atomic mass, which is the weighted mass for all isotopes in that of that element. Explain how the isotopes below carbon-12 and 14 are similar but different. Include the following in your response: proton, neutron, electron, mass number, atomic mass, atomic number, and isotope. Okay. So these are 2 isotopes, isotope 1 and isotope 2, and I know that because they have 2 different mass numbers, right? So I've used isotope. And carbon-12 and 14 both have 6 protons and 6 electrons in a neutral atom because you never change the number of protons. But carbon-12 has 6 neutrons because 12, the mass number, 12 minus 6, the atomic number, gives me the number of neutrons, 6 neutrons in carbon-12 and 8 neutrons in carbon-14, right? And atomic mass is just the weighted average of all these isotopes, right? And whatever other isotopes exist. Oh, and I said neutron. So carbon-12 has 6 neutrons, carbon-14 has 8 neutrons. Hopefully y'all will have that skill by tomorrow or by Wednesday. Okay, and on to the next page. All right, here we go. All right, Peter, Paul, and Mary are having an argument over the newest elements added to the periodic table. Peter and Paul say that elements X and Y are isotopes. Mary says that elements X and Z are isotopes. Who is correct and why? All right, so Peter and Paul say that X and Y are isotopes. So they say this and this are isotopes. Well, I see a different number of protons for each of these two things. So Peter and Paul are wrong. And Paul are wrong based on number of protons. X and Y are not isotopes because they are not the same element. I can actually look this up because I know, well, I can't look this up because we don't have element number 120 out here. But I know that these two are not the same element. They cannot be isotopes of each other because they have different numbers of protons and the same number of neutrons. And the same number of neutrons doesn't tell me anything, nor does electrons. But Mary is correct because she says that X and Z are the same, and they are isotopes because they have different numbers of neutrons. So Z has 140 neutrons, X has 141 neutrons, but they have the same number of protons. So Mary is correct because X and Z have the same number of protons and different number of neutrons, differing numbers of neutrons. Okay, and which isotope for an element will have the greatest effect on the average atomic mass? Well, I'm going to save that for just a second. So we're going to put a pin in this guy until we go down here and do this one. And we're going to see which isotope for an element will have the greatest effect on the average atomic mass. All right, so I'm going to do this guy down here. And the first thing I do when I'm calculating average atomic mass is, explain how to calculate average atomic mass, number the steps. All right. Step 1, change percents to decimals. Step 2, multiply mass number or exact mass times converted percentages. Converted percentage. Step 3, add all answers for each isotope. So you'll multiply a mass number or exact mass times a converted percent for each isotope, and then I'll add all answers. Okay, so now that we know the steps, step 1, I'm going to move this decimal 2 places to make it a decimal, and I'm going to move this 2 places to make it a decimal. Step 2, I'm going to multiply times my mass number for this one, 35 times 0.7577, enter, equals 26.5195. And chlorine, 37 times 0.2423, enter, is 8.9651. And when I add them together, 26.5195, I get 35.4846. Now let's look. This one accounted for 26 of these 35 AMUs. This one accounted for 8. So which one had the greatest effect on the average atomic mass? It is the highest percentage one. It is the most abundant. So most abundant percent isotope has greatest effect on atomic mass. That's why. Show your calculations, circle your answer. The most abundant. So, which isotope for an element will have the greatest effect on the average atomic mass of the element? The most abundant isotope. Whatever has the highest percentage is going to have the greatest effect, right? If tests are 40% of your grade, they're going to have the most effect on your grade, aren't they? If this has an abundance of 75%, it's going to have the most effect on the average atomic mass. Okay, now this next one, if you notice 78.99% is 79% plus 32%, we're already over 100%. So this one, the calculation is still the same. I would still convert, and then multiply. But here's the thing. I don't care what your answer is because your answer is going to be uncheckable. It's going to be over 26. And your answer ideally shouldn't be in between your lowest mass and your lowest mass number and your highest mass number, 35.486. This is definitely in between those two, right? Closer to 35. Why do you think? Because it's got a higher abundance percentage. So that's why I'm not even going to calculate this because you're going to get a ludicrous answer. I don't care what answer you get. You can calculate it all out. You can add it all up. I'm reckoning that it probably adds up to 28 something, some blah, blah, blah answer. Explain the difference between fission and fusion. Which process will produce nuclei that are heavier than hydrogen? Well, fusion will. And fusion is taking two lighter nuclei like hydrogens. If I take two hydrogens and I smash them together, then I make a helium, and these are two hydrogens. So how do I make nuclei that are heavier than hydrogen? By fusion. Fission is the exact opposite. It's where I take heavier elements and I bust them apart and make lighter elements or lighter nuclei. Draw a model representing fission and fusion. Well, I just did. I have two hydrogens. I smash them together. And what I get out of it is a helium. Right? Right. Fission, I can do just the opposite. I can take a helium and I can smash it apart and make two hydrogens. And this is fission. This is fusion. Fusing things together. Hopefully everybody gets those correct. All right, next video.